Hey everybody, I had to move there. Welcome to Definite Integrals. We're going to be talking about left Riemann sums today, and it's so similar to the midpoint and right Riemann sums for how to do all of this that this will be pretty quick. This is Flipping with Bennett, so let's go ahead and get started. When we talk about the area under a curve, for using left endpoint rectangles, this is the formula that we're going to use. It's b minus a over n, okay? N is the number of rectangles that they want you to use, okay? F of x sub 1 is the height, so this is the width of the rectangle. They call it delta x sometimes. But f of x sub 1, f of x sub 2, f of x sub 3, those are the heights of each rectangle. And notice we're going to be using all but the last endpoint on the right. So that's really important because when we talk about right, we use everything but the left. The last left one. So we're going to use all but the last right endpoint. So let's go ahead and get started. So I've got this first rectangle here, okay, and we're going to approximate the area under the curve of x squared from 0 to 4 using 4 left endpoint rectangles. So we're going to be using 4 rectangles. And notice here's the picture, okay? And we got 4 rectangles here, and I want you to pay attention. There's some gaps here, okay? So this probably won't be a great area that we're going to find. We're going to find it. And notice how we plug in 1, 2, 3, okay, and up to 4, the left endpoint of the rectangle is on the curve, okay? So the red curve there is x squared. So let's go ahead and take a look at how we do this. Okay, so number one, they're telling us that we have x squared as our function, and we're going from 0 to 4. Okay, so we're going from 0 to 4, and whoops, and we're using n equals 4 subrectangles. So delta x, the width of the rectangle, is b minus a over 4. In this case, b minus a over n. So we're going to have 4 minus 0 over 4, which equals 1. So that tells me the width of each rectangle is 1. So what I'm going to do here is I'm going to go ahead and start. Well, they said we start at 0. The length of that one rectangle is 1. So then the next rectangle's length goes from 1 to 2, and then from 2 to 3, and then from 3 to 4. Now, since we're using left endpoints, okay, these are the endpoints that are going to be my f of x1, f of x2, f of x3, that sort of thing. And notice how we leave all but the last endpoint. So this would be used if we were using left. If in the next video I wanted to use right, I'd be using these, okay? And then if I was using midpoint, I'd be going right in the halfway between. So it's all the same. These 3 techniques are going to be very similar. Okay, so I have now my area is going to be equal to 1 times, I've got to plug all these values in. They're all the same widths of the rectangle. So f of 0 plus f of 1 plus f of 2 plus f of 3. All those values plugged into my function. So I have 1 times f of 0 is 0, 0 squared, plus 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9. Okay, so my area is going to be 14. That's the area using 4 subrectangles. So what happens if I change this? What happens if, so the area is 14. What happens if I change this to let's say 8 rectangles? So notice I've gone now from 4 to 8 in the second example of the same function. Okay, we're going to be using x squared. Okay, but now we have 8 rectangles. And notice the left endpoints are all here. Okay, so x squared from 0 to 4, same interval. So let's look what happens. And notice there's still some gaps there. Okay, but let's see what happens when we go through this. So we've got to change delta x. Delta x is going to be b minus a. So 4 minus 0 over, not 4 this time, over 8. So our rectangles, instead of being a length of 1, are now a length of 1/2. So notice how there's 8 endpoints. Guess what? Guess how many things I'm going to be plugging in. Look, we're going to go from 0 to 1/2, 1/2 to 1, 1.5, or excuse me, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, 3 to 3.5, and 3.5 to 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 rectangles. Okay, and now I have eight rows here. So again, if I'm using left Riemann sums, I'm using all of these into my function. If I was using right, I'd be using those, and midpoint would be the halfway point. Okay, so those are the rectangles I'm using. So let's look. Area is going to equal 1/2. That's the width of all of the rectangles. So I put that out front of f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 and f of 3.5. Almost didn't make it. Okay, all of those. That's 3.5 there. Man, that's a lot. Okay, so now I plug all of those in, which I have. And so I have 0, f of 0, plus 1/2 squared is 0.25, plus 1 squared is 1, plus, let's go ahead and finish this off, 2.25, plus 4, plus 6.25, plus 9, that's f of 3, plus 3.5 squared is 12.25. And I take now half of 35. When I add all those up, I get 35, and I get 17.5. So the number's climbing. Okay, it's actually the more rectangles you use, the better it is, the more accurate it's going to be. So there is 2 examples using left Riemann sums. But what happens if we don't have a graph? Okay, so in my last example here, this is more common what you're going to find on the AP. The function is continuous function. So look at our table. Okay, continuous on the closed interval 2 to 13. Okay, it has values shown in the table using the intervals 2 to 3, 3 to 5, 5 to 8, 8 to 13. What is the approximate area under the curve by a left Riemann sum? So this is interesting because now the rectangles are different lengths. And I could have another video on this too. So we're not going to use the delta, the b minus a. The only thing that we know is we're not going to be using this last value. So if I think about it, if I start here and go down, here and go down, here and go down, here and go down, I can do that. So watch what happens. So I need the width of the rectangle. Well, that first rectangle, 2 to 3, so 3 minus 2, that's a width of 1 times. So I look at the L. I kind of go from here over and down. This f of x value is the height, and this is where we're getting our widths from. Plus, the next rectangle is 5 minus 3 times the height, 5 minus 3 times 4, plus the next one is 8 minus 5. That's the width of 3 times the height, which is -2. Okay, more about that later. Plus, the last one is 13 minus 8 times 3. So 13 minus 8, and I go down. Okay, there's my pattern. So I get 1 plus 8 minus 6 plus 15 when I simplify this out. 2 times 4 is 8. 3 times -2 minus 6. Okay, 5 times 3 is 15. So the total area there under that curve is going to be 18. So if you guys have any questions or comments about the area under the curve using left Riemann sums, you can type them below. We'll see you next time.